In the history of mathematics, a great deal of mathematics was invented to solve problems that arose from gambling and other games of chance. Here's a problem that you might have even considered yourself. Suppose two baseball teams are playing a best-of-7 series and your team is winning 3-2. Now, assuming the teams are equally matched, what are the chances that your team wins the series? In 1654, the French mathematician Blaise Pascal was asked to solve a very similar problem called the problem of points. The general problem posed to him was this. Suppose players A and B are playing a game of chance. Each game is worth 1 point, and whoever reaches n points first will win a prize worth D dollars. Each game is equally likely to be won by A or B. Currently, player A has A points, and player B has B points. If the players decide to stop playing the match at this point, because of rain or whatever, then what is the fair way to split the money? So, for example, suppose A and B are flipping a fair coin. Each time the coin lands heads, A wins a point. Each time the coin lands tails, then B wins a point. Whoever reaches a score of 10 points wins $100. Currently, A has 9 points and B has 8 points when they decide to stop playing. What is the fair way to split the $100? All right, so how would you solve this? Here are some plausible answers. You might say, well, you told me that those players were equally matched, so maybe they should split that $100 50-50. But then, of course, that doesn't take into account A's advantage. A is winning 9-8. So then you might say, well, then maybe we should split the money, split the $100 proportionately 9-8. Or you might look at it from the fact that player A has 1 game to go, player B has 2 games to win. So since player B has twice as many games to win as A, maybe A should win twice as much money as B. Maybe that pot should be split 2-1. All of these answers seem plausible, but they all lead to paradoxes. If you can, and none of them are right. I'll give you the right answer later. But and if you figure this one out, then what if the score were 7-6 instead? How would you solve that problem? How would the answer change? To answer questions like this, Pascal developed the theory of probability and created Pascal's triangle. Behold Pascal's triangle. Pascal's triangle appears on the cover of many discrete mathematics textbooks. The triangle was actually known to mathematicians in China and India at least 500 years before Pascal. But Pascal was the first mathematician to systematically explore its many properties in his treatise Traité du triangle arithmétique, written in 1655. So let's look at Pascal's triangle, and you can immediately observe that it has ones on the borders of the triangle. The other thing to notice is that each entry is the sum of the 2 entries above it. For example, we see that above the 20, we have a 10 and a 10, right? What would the next row of Pascal's triangle look like? Well, it would have to begin and end with a 1. And then looking at the row above it, we see 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, and then that would create what we'd call row 7 of Pascal's triangle. Now, I'm actually going to write this triangle as a right triangle instead of the isosceles triangle that we saw. I do that because this will allow us to see some of its patterns more clearly. And besides, to excuse the pun, the right triangle is just the right way to draw the triangle. Okay, so along the right triangle, you see that we have ones down the leftmost column. And if we go to the column after that, we have all the integers in a nice row. In a nice, I shouldn't say in a row, in a column, right? 1, 2, 3, 4, 5, 6, and going on forever. If we go to the next column, we have what are called the triangular numbers. 1, 3, 6, 10, 15. Where do these numbers come from? Why are they called triangular numbers? Because you see, if you were to draw triangles by successively writing dots of length 1, 2, 3, 4, and so on, then the number of dots in the triangle would be 1, 3, 6, 10, 15, and so on. That's why they're called triangular numbers. Here's another pattern that you may not have seen before. If you go down that third column, you see that 1 plus 3 is 4, and 3 plus 6 is 9, and 6 plus 10 is 16, and 10 plus 15 is 25. We get perfect squares. 4, 9, 16, 25, and that goes on forever. How about the column after that? Well, these are numbers that can be described as sums of triangular numbers. These are called the tetrahedral numbers because you can create them, as in this graphic, by summing up dots that occurred in filled-in triangles. Okay, so what is Pascal's triangle really? How do we define it? How do we prove its patterns? I mean, I've only shown you some patterns for a few handful of rows. How do you know that things don't just go kablooey after that? Okay, so here is the official definition of Pascal's triangle. All right, so for n greater than or equal to 0, and in discrete mathematics, we always start at 0, the nth row of Pascal's triangle is, it's starting on the left with n choose 0, then n choose 1, and then n choose 2, all the way up to n choose n. Now let's remind ourselves what these n choose k's are. These are the binomial coefficients. What does n choose k count? Among other things, it's the number of ways from a class of n students to create a committee of size k. That's what n choose k counts. We have a formula for it. So here would officially be Pascal's triangle, where the entry in row n, column k, is n choose k. And when I expand those out numerically, we get our old friends 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. It's the triangle. Now, again, do you trust me? You've only seen rows 0 through 6. How do you know that it will continue to work after that? Well, let's first explore, I'll get to that in a minute, but let's first explore some other patterns. For instance, we see if you read across any row of Pascal's triangle, it reads the same way if you go from left to right as if you go from right to left. So for instance, row 4 is 1, 4, 6, 4, 1, whether you read that forwards or backwards. That's because 4 choose 0, the number on the left, is the same as 4 choose 4, the number on the right. Both of those are equal to 1. And 4 choose 1 and 4 choose 3, as I go 1 in, those are both equal to 4. And in general, I claim that n choose k will be the same as n choose n minus k. And let's prove that. Okay, so we don't have to just rely on a simple pattern. We'll know that it's true not just for the first 6 or 7 rows, but for all rows thereafter. The algebraic proof is pretty straightforward. We have a formula for n choose k. So what if I replace k with n minus k? What do we get? We'd get n choose n minus k is n factorial over n minus k factorial n minus k factorial, which simplifies to n factorial over n minus k factorial, which is the same as n choose k. A pretty straightforward algebraic proof, but I think that there's a better proof that doesn't require any algebra at all. It's called a combinatorial proof. We just ask, what are those things counting? That both quantities, n choose k and n choose n minus k, are counting the same thing. For instance, why should 4 choose 1 be the same as 4 choose 3? Well, 4 choose 1 counts the ways from a class of 4 students to ask 1 student to stand up, which is the same as from a class of 4 students asking 3 of them to sit down. There's many ways to pick 1 thing out of 4 as to pick 3 things out of 4. And in general, the number of ways to choose k objects out of n, which can be done n choose k ways, is the same as the number of ways to not choose n minus k objects out of n, and that can be done n choose n minus k ways. So we would know this theorem was true even if we didn't have a formula for n choose k. How do we know that each row and column is going to begin and end with a 1 using our n choose k definition? Well, simply because every row is going to start like n choose 0 in the form n choose 0, and every row is going to end as n choose n, and both of those we know are equal to 1. What about in between? We've seen that every number is the sum of 2 numbers above it. So the pattern that we see on Pascal's triangle is when we look in row n and the kth entry, that it's equal to the number directly above it, that would be row n minus 1, the kth entry, plus the number just to the left of it, that would be n minus 1 choose k minus 1. So the pattern that we're seeing here in the triangle is that n choose k seems to be equal to n minus 1 choose k plus n minus 1 choose k minus 1. Now, there are 2 ways of proving it. One, we could do it algebraically. We could express those in terms of factorials. And for those of you that like to add fractions, you can do it algebraically. I'll just flash it right here. There's a much nicer proof, though. This is my favorite kind of proof, called a combinatorial proof, by showing that both sides of this identity, n choose k and n minus 1 choose k plus n minus 1 choose k minus 1, are counting the same problem. You'll notice, by the way, that I spelled combinatorial with some of the letters highlighted. The reason, in fact, my students sometimes call these things cool proofs. My conjecture is that this is actually where the word cool comes from. That it just became too cumbersome to keep saying, wow, that's really combinatorial. So cool was just the natural thing to say. But I digress. So here's a question. From a class of n students, how many ways can you choose a size k committee? Now you say, well, Professor Benjamin, we've known that since lecture 2. It's n choose k. And I'd say you're right. Now comes the fun part. Take that same question and answer it on the right-hand side. Why should that answer also be n minus 1 choose k plus n minus 1 choose k minus 1? I'll tell you why. This is a technique I sometimes refer to as weirdo analysis. Okay, you've got this class of n students, but let's suppose student n, the student sitting way in the back of the classroom, has bad breath or something. And I ask, how many of these committees do not use student n? Okay, so from this class of n students, I'm going to pick a size k committee. If it doesn't use student n, then I can choose that committee n minus 1 choose k ways. Pick any k students from 1 to n minus 1. Plus, the next question, how many of these committees do use student n, must use student n? Well, here, since student n must be in the committee, from the remaining n minus 1 students, I have to choose k minus 1 to join the committee. Therefore, altogether, there are n minus 1 choose k committees that don't use student n, plus n minus 1 choose k minus 1 committees that do use student n. Which answer was right? Answer 1 or answer 2? They both were right. Our logic was impeccable both times. Therefore, the 2 problems have to have the same answer. So here are other gorgeous patterns of Pascal's triangle. If we sum across the rows of Pascal's triangle, what do we see? We see that the first row sums to 1. The second row sums to 2. The third row, 1 plus 2 plus 1, sums to 4. The next row sums to 8, 16, 32. The pattern is inescapable. These rows are summing up to powers of 2. In fact, if you look at row 5, you see that row 5 is summing up to 32, which is 2 to the 5th power. So the nth row of Pascal's triangle clearly appears to be adding up to 2 to the n. And if you express the numbers in Pascal's triangle according to their definition as binomial coefficients, what that fifth row is saying is that 5 choose 0 plus 5 choose 1 plus 5 choose 2 plus 5 choose 3 plus 5 choose 4 plus 5 choose 5 must equal 2 to the 5th. And in general, n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n appears to be equal to 2 to the n. By the way, saying all these sums and chooses can be a mouthful. A notation that is used frequently in discrete mathematics, it's called sigma notation. We'll only use it sparingly, but you should see it. It says, to express the same theorem, we say the sum of n choose k, as k goes from 0 all the way up to n. That's what the sigma with the 0 on the bottom and n at the top represents. It's the sum of n choose k as k goes from 0 to n must equal 2 to the n. Here's a combinatorial proof of that theorem. So what's the question whose answer is n choose 0 plus n choose 1 all the way up to n choose n? Well, here's a simple question. From a class of n students, how many ways can I create a committee of any size? We know the number of committees of size k is n choose k, and the committee size k can be as little as 0 or as high as n. So in total, we have n choose 0 plus n choose 1 all the way up to n choose n. Great! What's another way of answering that question? Another way is to say, well, to create a committee of any size, I'm going to go through the classroom one student at a time. And I look at student 1 and I decide yes or no, are they on that committee or not? Yes or no to the second student, yes or no to the third student, yes or no to the fourth student, all the way up to the nth student. So the total number of committees, since I have two choices, n times is 2 to the n. Again, since we came up with two different answers to the same counting question, those answers must be the same. You might recall from algebra that the binomial theorem was stated this way. If you take the quantity x plus y squared, you get x squared plus 2xy plus y squared. For some people, that's all the algebra they remember. X plus y cubed is you might remember, is x cubed plus 3x squared y plus 3xy squared plus y cubed. You probably don't remember x plus y to the fourth is x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. To extend the pattern backwards, x plus y to the first power is x plus y, and x plus y to the 0th power is 1. Now, if I throw away all those x and y's and I just look at the coefficients behind them, you see we have the same coefficients that appear in Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. Where do these come from? This is the classical binomial theorem. And this was recognized historically long before Pascal. People saw this as a fundamental identity, that x plus y to the n is the sum of n choose k, x to the k, y to the n minus k. Even the binomial theorem has a nice combinatorial proof. Let me give it to you here. Suppose you have a room with x girls and y boys. I say it in that order to be biologically correct. And suppose we have n distinct pieces of candy. I got a lollipop, I've got a Tootsie Roll, I got a piece of licorice, whatever. How many ways can you allocate these n different candies to the X girls and Y boys? And yes, some of the kids may end up empty-handed. Maybe one kid gets all n pieces of candy. That's allowed by these rules. How many ways can we allocate the candy? Well, the first answer is, well, each piece of candy, there are x plus y places it could go. It could go to any boy or girl. So the first candy, there's x plus y choices. The second candy, x plus y choices. And so on down to the nth candy, x plus y choices. Therefore, we get x plus y to the n. On the other hand, now I say I'm going to take that same problem, but I'm going to first count how many ways can you allocate the candy so that the girls get exactly k candies. All right, how could you do that? Well, first you say, well, from those n pieces of candy, let's decide which k of them are going to go to the girls. So we're going to create a girl pile of candy and a boy pile of candy. Right? So how many ways can I choose which are the girl candies? N choose k ways. And now once I've separated them into my piles, now how many ways can I allocate the girl candy? Well, each piece is now going to have x choices. So I've got k candies for the girls, each of which there are x choices. So there's x times x times x, x to the k ways. How many boy candies do I have? I have, since there were k girl candies and n candies altogether, there had to be n minus k boy candies. And each of those boy candies, there are y choices for where each of those goes. So y choices times the first, y choices for the second, y choices for the last, y to the n minus k altogether. Therefore, the number of ways of allocating the candies where the girls get exactly k of them is n choose k, x to the k, y to the n minus k. If I take this all together, if I sum these over all possible k from 0 to n, that gives me the right side of my identity, which is the right side of the binomial coefficients. Earlier, we showed that the sum of n choose k, as k goes from 0 to n, is 2 to the n, right? N choose 0 plus n choose 1 plus n choose 2 up to n choose n was 2 to the n. And we had a beautiful combinatorial proof for that, but there's a really slick proof using the binomial theorem. In fact, it's literally as easy as 1 plus 1 equals 2. Check it out. Here's the binomial theorem. If you let x equal 1 and y equal 1, then 1 plus 1 to the n is 2 to the n. And the other side of the binomial theorem says that's the sum of n choose k, 1 to the k, 1 to the n minus k, so the 1's disappear, and I just get the sum of n choose k. Here's another important pattern that appears in Pascal's triangle. We know that the nth row sums to 2 to the n. What if I skipped along? What if I added every other number in Pascal's triangle? Then what would we get? It may not surprise you that you get exactly half the total you had before. Instead of every other number in row n summing to 2 to the n, it sums to half of 2 to the n, or 2 to the n minus 1. Like, for instance, that's row number 6. That says 6 choose 0 plus 6 choose 2 plus 6 choose 4 plus 6 choose 6 is equal to half of 2 to the 6th, 32. And since the sum of the even position numbers is half, then that means the sum of the odd position numbers must also be a half. 6 choose 1 plus 6 choose 3 plus 6 choose 5. Putting that all together, we get the sum of the 6 choose evens equals the sum of the 6 choose odds. If you interlace them and add them and subtract them, what you get is that the alternating sum of 6 choose k is equal to 0. In fact, the alternating sum is not just true for 6, but of any number n, the alternating sum of n choose k is equal to 0. You actually can do that one using the binomial theorem too. Whereas the earlier proof was as easy as 1 plus 1 equals 2, you can actually prove this one as easy as doing negative 1 plus 1 equaling 0. I'll leave that one as an exercise for you. You can also prove that theorem combinatorially. Let me mention a few other really pretty patterns that appear in Pascal's triangle. If we sum along the columns of Pascal's triangle, you can't sum all the way down because they go on forever. You get infinity. But if you sum part of the way down, you get what's called the hockey stick identity. And I'll just illustrate it here. Notice you have 1 plus 2 plus 3 plus 4 is equal to 10, which is the next number off to the side. Or here, 1 plus 3 plus 6 plus 10 gives us 20. And this pattern exists throughout Pascal's triangle. You can prove that one combinatorially too. You might want to try that one as an exercise. Beautiful patterns in Pascal's triangle. Here's another one that I love. If I asked you how many odd numbers appear in Pascal's triangle, then the answer turns out to always be a power of 2. And not just any power of 2, but I just got to tell you the answer. It's 2 to the number of 1s in the binary expansion of n. So for instance, if I'm looking at row 83, how many odd numbers will it contain? Well, 83, when you write it in terms of powers of 2, it's 64 plus 16 plus 2 plus 1. It's going to have this as its binary, its base 2 representation. There are 4 1s in it, and therefore row 83 will have 16 odd numbers. If you draw a picture of where those odd numbers are, you also get a beautiful picture, also known as Sierpinski's triangle. So let's recall from lecture 2 the following question. If a fair coin is tossed 10 times, what is the probability of getting exactly 3 heads? Okay, we saw earlier that the answer to that was that there were 2 to the 10 ways of flipping the coins, and 10 choose 3 of them resulted in exactly 3 heads. So we can answer that question just from what we know. But now suppose I ask you the following biased question. Suppose that our coin is biased in such a way that the probability of heads is 0.4, and therefore the probability of tails is 0.6. If the coin is tossed 10 times, then what's the probability that we get exactly 3 heads? Now, the probability that we see 3 heads in a row followed by 7 tails in a row is equal to 0.4 cubed times 0.6 to the 7th, because each of those probabilities has outcomes has probability 0.4 or 0.6. And since they're independent, one coin flip doesn't affect the other, we multiply those probabilities together. So is that the answer? Well, not quite, because that wasn't the only way to get exactly 3 heads. There were how many ways to get 3 heads? 10 choose 3 ways to get 3 heads, each of which has probability 0.4 cubed times 0.6 to the 7th. And when we multiply that out, we get our answer of 0.215. Problems like this are actually called binomial probabilities. And again, the reason they're called binomial is each trial, each flip of the coin, has 2 outcomes, heads or tails, success or failure. Let's get back with the problem of points that Pascal considered. Okay, so again, where we left off, A and B were flipping the coin. Whoever reached 10 points wins $100. Currently, A has 9 points and B has 8 points. How should that $100 be split? The answer is that they should split it $75 to $25. Okay, that $100 should be split 75-25. Why? Pascal actually gave 3 reasons for this problem. One way he did was he said, let's think of this recursively. Let's reduce this to a smaller problem. Right now the score is 9-8. And let's consider the next flip. If A wins the next flip, which he will with probability of half, then the score will be 10-8 and A wins the $100. On the other hand, if B wins the next flip, also with probability of half, then the score is 9-9. And then how should you split the $100? Well, everyone in the world would agree that if the score is tied, you should split that $100 50-50. Okay, therefore, half the time A deserves $100, half the time A deserves $50, taking the average of those two gives us $75. Here's another way to consider that, to solve that problem, by using what's called expected values. Currently, the score is 9-8. Now, consider the next flip. If A wins the next flip with probability of half, then what's the chance that he wins the game? He wins the match. 100%. If B wins the next flip, then what are the chances that A wins the match? Well, the score will be 9-9, so A will have a 50% chance of winning the match from there. So overall, the probability that A wins is the average of 1.5, which is 3/4. So A wins the match with probability 3/4. B wins the match with probability 1/4. Since A is 3 times as likely to win as B, A should be paid 3 times as much as B. And to get a 3-to-1 payout, A should get $75 and B should get $25. Here's Pascal's third approach. Consider the approach of equally likely outcomes. Currently, the score is 9-8. How many more games is this match going to last? It might take one match, it might take one game, it might take 2 games. Let's insist that both of those players play their games, even if A wins on the first game, that everybody has to play 2 games. Okay, we have to play 2 games. So then there are 4 possible equally likely outcomes, right? Either A wins first and A wins second, or A wins first, then A wins the first game, then B wins the second game, or B wins the first game and A wins the second game, or B wins the first game and B wins the second game. All of those have the same probability of happening, but A wins 3 of those outcomes, B wins 1 of those, and therefore A should be paid in a 3-to-1 ratio just like before and get $75 to $25. Here's the new score. Suppose instead that the score is 7-6. A needs 3 games, B needs 4 games to win. How many more games is this match going to last? It's going to last at most 6 more games. So let's insist that they play all 6 games. Now, there are 2 to the 6th, 64 possible equally likely outcomes, just like the flip of a coin 6 times. Among these outcomes, A is going to win the match if he can win 3 or 4 or 5 or 6 of these games. If he wins 3 or more, he wins the tournament. How many of those 64 outcomes does he do that? By definition, 6 choose 3 plus 6 choose 4 plus 6 choose 5 plus 6 choose 6. Sum those numbers. A wins 42 of the times. B wins the other 22 of the times. Therefore, in order to do this, Pascal invented his triangle to see that A is going to win with those 4 numbers on the 6th row of Pascal's triangle, and B is going to win with those 3 numbers on that row of Pascal's triangle. That's your 42 to 22 advantage. So A should be paid 42/64 of the money. B should be paid 22/64 of the money. That amounts to $65.62.5 for A and $34.37.5 for B. You may wonder how A and B should determine who gets that extra ½ cent. My guess is if they asked Pascal, he'd tell them, go flip a coin.